In section 3.7, we want to take the ideas that we developed over the course of the first 3 sections of this chapter, the ideas of increasing, decreasing, concavity, all that kind of stuff, and use them to get fairly accurate graphs of functions by hand. However, before we can do that, we need to talk about something first. We're going to be talking about asymptotes, and we're going to be using limits to do so. First, we'll start with vertical asymptotes. We've actually already kind of seen these a little bit already, but we're going to actually make a definition here. We're going to say a vertical asymptote so we say a function f has a vertical, which I'm going to abbreviate these. Vertical asymptote, let's say, instead of at, let's say of x equals c. So here, this is a vertical line, x equals c, if either of the one-side limits of f at c are plus or minus infinity. We don't care whether or not it's positive infinity or negative infinity, and we don't even care if it's only on one side. We could have a situation. Actually, I'm not even going to draw the axis here. We could have a situation where, say, it goes up on one side and comes from the other side on there, or we could have maybe they both go to positive infinity and both go to negative infinity, or we could even have a situation where, let's say, the function comes and goes to a point, but on the other side, it actually goes to positive or negative infinity. Any of those are possibilities, and these will be vertical asymptotes in any case. Just as long as one of the one-side limits, so it goes to, on one of the sides of C, it goes to positive or negative infinity, then we're going to consider it a vertical asymptote. So let's actually talk about these infinite limits and look at some examples of when that occurs. Let us start with problem 8. We're going to look at the limit as x goes to negative 5, but specifically from the negative side, so we're talking about a one-side limit here, of the function 1 over x plus 5. And they're claiming here, in our instructions, well, I guess they're just saying find the limit, but they're bringing this up because we're expecting to have a limit of either positive or negative infinity. And why would that occur? Well, think about what would happen if we try to plug in negative 5. If we try to plug in negative 5, the bottom here becomes 0. And that is going to force this thing, because we're taking 1 divided by really tiny numbers, we're going to end up blowing up and get some version of infinity. That doesn't tell us which version of infinity we get, though. If we're dividing 1 by very big, by very small positive numbers, we're going to get really big positive numbers. But if we take 1 divided by really small negative numbers, we're going to get really big negative numbers. In other words, on one side, in one of those situations, we're going to be going to positive infinity, and the other situation, we're going to go to negative infinity. And we want to figure out which one's which in this particular case. Now, the book actually doesn't really get into exactly how we would determine that. It thinks, well, we could ask you to graph it, but that's kind of begging the question because we want to use the results to draw the graphs in the next section anyways. Or we can plug in values close to negative 5 and see what happens. But unfortunately, that can be a little bit misleading. That's not very precise. So we want to think about some other ways of being pretty sure exactly what's happening here. So we have 2 situations here. Let's say at negative 5, maybe we have it going to positive infinity. We're only looking at one side of it. We're looking at the side where we're on the left-hand side, or the negative side of negative 5. We could have it going to positive infinity over there. Or we could have it going to negative infinity. Those are two possibilities. What are different about these possibilities other than the raw values of the function? Well, if it's going to positive infinity, this function has to be increasing as it approaches -5. Versus when it's going to negative infinity, it has to be decreasing. How about we determine where it is, whether or not it is increasing or decreasing when it gets close to -5? And we can do that using the first derivative. So if we call this our function f, they didn't name it, so let's give it the name of f. We'll take the derivative. Now this is really just x plus 5 to the -1 power, and we can use our chain rule here. That -1 comes out, we get a negative, and then the -1 changes to -2, which I'm going to write that as 1 over x plus 5 squared. Technically, also, we need to multiply by the derivative of the inside, but x plus 5 has a derivative of 1, so we don't really have anything more to multiply by. So our derivative here is -1 over x plus 5 squared. Note that this is never 0. We don't have to worry about any critical points where this equals 0. We also, it doesn't exist at -5, but that's going to be one of our asymptotes. But we can turn that into a number line for our first derivative. Of course, we're not really concerned with what's happening from -5 onwards. We're only concerned with this side of it. So I'm just going to pick a test point. Just go ahead and put in -6 into our derivative. Of course, that's going to give us this negative of 1 over, well, -6 plus 5 is -1, but we're squaring it, so actually that negative goes away, and we're overall left with a -1. In other words, our function is decreasing from -infinity to -5. Specifically, the only situation here is that we're going to -infinity. If it was going to positive infinity, this would have to be increasing. So our answer here is -infinity. So that's a fair amount of work just to determine it for this particular case. But unfortunately, this is a little bit of a complicated problem. Now, when we're actually going to be graphing functions in the next section, we're already going to be looking at the derivatives anyways. So this will be kind of a little bit more natural in those contexts. But if we're just trying to address a limit like this, it can be a little bit more complicated than you expect it to be. But that's just the way it is. Now, in some cases, it's not as bad. Let's look at problem 12. It's a very similar problem. They're actually asking for the same thing. We're looking at a limit. This time is x goes to -4. We're going to be looking at the positive side of it this time. And then the function here is 1 over x plus 4 squared. Similar to what we had up here, if we try to plug in -4 right away, we're going to make the denominator 0. And so we're going to be going to either positive or -infinity. We could go ahead and look at whether it's increasing or decreasing and all that kind of stuff. But notice that whatever values we plug in here, aside from -4 itself, we're going to get a positive number on the bottom, because the square is going to get rid of any negative we would have had anyways. So this function, no matter what value we plug into it that is in this domain, is always going to result in a positive number. This function cannot go to -infinity. It would have to go through some negative numbers to get there. So the fact that we know that there's going to be an asymptote at -4 means that the only possible outcome is that this is going to a positive infinity. So let me just, this is going to positive infinity since this is never negative. So pay attention to those kind of things where you can already just guarantee that your function is going to be either positive or negative in a particular case, and you can kind of skip this whole idea of having to figure out whether it's increasing or decreasing. Avoid having to take the derivative in, because that's a little bit more complicated. Let's use these ideas to find some vertical asymptotes. We'll look at problem 16. Here they give us a function. I actually named it for us this time. The function x squared plus 2x minus 35 divided by x squared minus 25. Now remember, the key point in the last two problems for us being able to determine that we actually did have an infinite limit, either positive infinity or negative infinity, was that the denominator went to 0. If the denominator doesn't go to 0, then we're going to have some number on top divided by some non-zero number, and we're good. We don't have to worry about it. So therefore, all we need to do to determine where there could be a vertical asymptote is look at where the denominator is actually equal to 0. In other words, when is x squared minus 25 equal to 0? Well, if I go ahead and solve this, and it's relatively easy to solve, we have x squared is 25, or x is either positive or negative, don't forget the negative one here, of 5. Square root of 25 is 5. So x equals 5 and x equals negative 5 are the possible vertical asymptotes. But we do have to be a little bit careful. Just because these make 0 on the denominator does not mean that they are vertical asymptotes. If the numerator is actually 0 at one of those points, we could end up with a non-infinite limit. So we're going to actually test whether or not the numerator is equal to 0 at 5 and negative 5. Let's start with negative 5. F of negative 5, well, I shouldn't say f of negative 5. The numerator at negative 5, we have negative 5 squared plus 2 times negative 5 minus 35. This is a positive 25 minus 10 minus 35. We actually get a negative 20. So what we can already say here is that we do have a vertical asymptote at x equals negative 5. What about 5? If we plug 5 into the numerator, we have 5 squared plus 2 times 5 minus 35. This time is 25 plus 10 minus 35. We do get 0. So at x equals 5, we may or may not have vertical asymptote. Let's actually look at the limit. What is the limit as x goes to 5 of our function? Now, in the cases where we do actually have, we know that the numerator and the denominator both go to 0 as we go to that point, and we're dealing with polynomials on the denominator and numerator. In other words, we have a rational function. That means that we can actually immediately know that we can factor something. Basically, the fact that putting 5 into this polynomial on top means that x minus 5 has to be a factor of the top. X minus whatever the number we plugged in has to be a factor. Same thing on the bottom. X minus 5 has to be a factor of x squared minus 25. The other factor we can usually get pretty easily. So we know that x here times whatever version of x we have here has to be an x squared. So we're going to get just an x. Same thing on top. We're going to get an x squared by multiplying x and x. Then to get negative 35, we're going to take negative 5 times something. What times negative 5 equals 35? It's a 7. Same thing down here. What times negative 5 equals negative 25? It's a positive 5. Now, actually, we already knew that positive 5 here, because x minus a negative 5, we knew had to be a factor. But the point here is that use the facts that we already know to be able to simplify the factorization part. Now, why do we want to factor out x minus 5? Because it cancels. I mean, that's kind of the whole point, is that we knew that x minus 5 had to be a factor of both of them because we got 0 on both of them. And so really we're just taking the limit of x plus 7 over x plus 5, as x goes to 5, and this time we don't actually have a problem. We can plug 5 into here. 5 plus 7 is 12. 5 plus 5 is 10, which I guess we could simplify to 5 or 6 over 5. In other words, we do not have a vertical asymptote at x equals 5. We actually have a limit, a non-infinite limit. And remember, our definition specifically says that we have to have an infinite limit on at least one of the two sides. Here, we know that on both sides, the limit is a finite 6 over 5. And so we do not have a vertical asymptote at x equals 5. Our answer is specifically this. Missed. That's our final answer for this problem, when they want us to find the vertical asymptotes of this function. Let's do another problem of this sort. We're going to look at problem 18. It's exactly the same instructions. We're still trying to find vertical asymptotes of a function. This time our function is x squared plus x minus 30 divided by 4x squared minus 17x minus 15. So the idea is really similar. All we're trying to do is figure out first, where is the bottom equal to 0? And then we're just going to see whether or not those possibilities are actually going to make a vertical asymptote. So I'm going to set 4x squared minus 17x minus 15 equal to 0. I'm going to try to factor this. Now, this is a little bit complicated one to factor, I admit. We do need to figure out what are the possibilities here. So the first thing here and the first thing here need to multiply to be a 4x squared. That could be, say, a 4x times an x, or a 2x times a 2x. Same thing, the last one here and the last one here have to multiply to give us a negative 15. That's probably going to be like a positive 3 and a negative 5, or a negative 3 and a positive 5. But it could also be negative 15 and 1, or 15 and negative 1. We kind of have to play around with all the different possibilities to see what gives us a negative 17 for our middle term. It turns out, after some playing around with it, I got a factor of 4x plus 3 and an x minus 5. Because then the 4x times a negative 5 gives me a negative 20, but then I add 3 to that. Negative 20 plus 3 gives me a negative 17. And this gives us possible places where this equals 0. Well, we have a 5 from here, and from here, we have to set this equal to 0 and solve. That means 4x has to equal negative 3, or in other words, x has to be negative 3/4. These are the two places where the polynomial on bottom is equal to 0. We're going to go ahead and plug these into our numerator just to see if they necessarily are going to be places that would have a vertical asymptote or not. If I plug negative 3/4 into there, we have negative 3/4 squared plus a negative 3/4 minus a 30. Now, it doesn't really look like it should come out to be 0. In fact, it comes out to be, what, negative 483 over 16. But the point is that it's not 0. So we definitely do have a vertical asymptote at x equals negative 3/4. What about 5? Well, if you plug 5 into the numerator, we have 5 squared plus 5 minus 30. We have a 25 plus a 5 minus a 30. And that actually does give us 0. So this could still be a vertical asymptote, but we're not sure at the moment. We're going to take the limit as x goes to 5 of our function just to see what happens. Now, actually, on the bottom, we already know how to factor that. We had a 4x plus 3 and an x minus 5. This just coming from here. On the top, we do know we have a factor of x minus 5, just because putting 5 in there gave it 0. we need to figure out what the other factor is. Of course, the first thing here, times x, has to give us an x squared, so you just get an x. And the last thing here, times negative 5, has to give me a negative 30. Well, that's going to have to be a positive 6. In other words, we can cancel out an x minus 5. We end up taking the limit as x goes to 5 of x plus 6 over 4x plus 3. X plus 6 when x is 5 is 11. Putting 5 into the bottom, we have 20 plus 3, or 23. In other words, we did not get infinity. So this doesn't mean that in every case where we do get 0 on the numerator, we actually do not have a vertical asymptote, but it is a place where we actually need to take our limit. So this is our answer for this particular problem. It's just that one line. Now I do want to do one more example, but I don't really have an example from the book to use here. I'm actually going to modify problem 15 a little bit. So here I'm going to give you a function where the top is x squared minus 8x plus 15. On the bottom, I'm going to have x squared minus 6x plus 9. We want to find out where the vertical asymptotes of this function are, if there are any. Now, there don't have to be any, but we kind of expect that there will be. Well, we're going to see where is this denominator equal to 0. We need to factor this, or you could use the quadratic formula if you want to. But it turns out this one factors pretty nicely as x minus 3 times x minus 3, or x minus 3 squared. Of course, that only equals 0 if x minus 3 equals 0, or in other words, the x has to be 3. There's only one number that makes the bottom equal to 0. Now, does 3 make the top equal to 0 too? We need to check that. So I'll take 3 squared minus 8 times 3 plus 15. We have a 9, we have a negative 24, and we have a positive 15. Well, 9 plus 15 gives us 24, so subtracting 24 from that does give us a 0. So we're not guaranteed anything about this being an asymptote or not. We're going to have to check our limit. What is the limit as x goes to 3 of our function? Well, of course, the top and bottom both have a factor of x minus 3 in there. We know the bottom actually is the square of x minus 3. So we'll go ahead and put that in there. On top, we know it has a factor of x minus 3 because 3 in that polynomial does give us a 0. Our other factor, when we need the first times x to be x squared, so of course we just have an x there. And the last times negative 3 gives me a positive 15. So I need to multiply by a negative 5. I can go ahead and cancel. We have 2 copies of x minus 3 on the bottom, so I'll cancel one of those with the factor of x minus 3 that's on top. And so I'm taking the limit as x goes to 3 of x minus 5 over x minus 3. Well, notice putting 3 in here does give us a 0 on the bottom, and it does not give us a 0 on top. That means that we do have an infinite limit here. We don't have a situation where we had a 0 on top to compensate for a 0 on the bottom. So this is either plus or minus infinity. It's an infinite limit of some sort. We don't know exactly what the behavior here is. Really, we should be taking one-side limits if we really need to know whether or not it goes to positive or negative infinity. And in this particular case, I already know that it does go to positive infinity on one side and negative infinity on the other side. So can't really say too much more than that this is an infinite limit. In other words, we do have a vertical asymptote of x equals 3. So the point here I'm trying to make is that when we have a rational function like this, you do want to find out where the bottom equals 0, see if we actually get 0 on top at those same points, and if we do get 0, it may be a vertical asymptote or it may not be. And this is a case where it actually was still a vertical asymptote. It kind of came down to the fact that we had multiple copies of x minus whatever c value we had on the bottom. So we didn't actually get to cancel out all the factors of that. And so they stayed a problem. But it's a little hard to tell that that's going to happen until you've actually done the limit. So be a little bit careful about that. But it all basically comes down to the same process every time. Well, that covers vertical asymptotes. We do have another type of asymptote that we're going to talk about. We're going to be talking about horizontal asymptotes. But we're going to have to spend a little bit of time actually talking about those. So we'll have that in our next video. So see you then.